Alrighty. Hello and welcome to the live OpenSSL webinar on application performance tuning with OpenSSL engineer Tomasz Mraz. My name is Kajal Subkota and I will be moderating this webinar. As a reminder to everybody, all attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you'd like to ask the question live, as we will host a Q&A session following the presentation. As a reminder, this webinar will also be recorded and made available on our YouTube channel shortly after the presentation. And if you'd like to receive a copy of the slide deck, please email us at marcom, that's MARCOM @openssl.org, and we'll be happy to send that over to you. And I invite everyone to follow us on all of our social media. So that's, Twitter, YouTube, LinkedIn, everything, which is just at OpenSSL _. And feel free to email us at feedback, that's FEEDBACK @openssl.org if you have any additional questions regarding the webinar or anything else regarding OpenSSL. And now I'm going to hand it over to Tomasz for the presentation.
So, hello everybody. Today we will be talking about application performance tuning. So what are the areas that will be covered today? I will talk about building OpenSSL for optimal performance. Then I will cover how to optimize EVP API usage, how to optimize Libssl API usage, and I will also talk a little bit about choosing the most performant and secure algorithms. The assumptions for the audience is that in the interests of time, this presentation assumes that the audience is familiar with coding applications in C. Audience has at least partially seen the previous webinar videos, and the audience has some knowledge of cryptographic algorithms and concepts, high-level knowledge. It doesn't require low-level deep knowledge. So let's start with building OpenSSL for optimal performance. How to build OpenSSL was covered in the first webinar we presented. The link is on the slide. One of the most important things is that you should avoid using NOASM. And for that, if you build on Windows, NASM must be installed. Support for MASM is not really up to date. You need to avoid using -d or -debug option for configure command because that disables optimization for the C code. It's useful to enable -ec_NSP_64_GCC_128 if performance of P521 and P384 curves on newer versions of OpenSSL for ECDH and ECDSA is important. This option, enabling this option, requires 64-bit little endian platform. Big endian support is going to be added in future. It's a good idea to disable engines if you don't need the support for them, and disable DH, which is the finite field Diffie-Hellman support. If the support is not needed currently, it should not be really needed because the ECDH is prevalent and basically all non-legacy devices support it. You can disable various other unneeded features, but it will not affect speed mostly. However, it can lower the footprint of the library in memory. By default, the CC option -03 is used for like maximum optimization for speed. But you can try adding -02 or -OS, as these might provide better performance for your concrete use case and platform. And last but not least, use the latest 3.x minor version, as the performance was improved significantly from 3.0 branch. And we don't usually backport performance improvements to stable branches because that would destabilize them. You can still use validated 3.08 and 3.09 FIPS providers with the latest 3.x version of library. You can simply build the FIPS provider and replace the FIPS provider from the current current library with the validated version, and that will make your installation performant and still FIPS compliant. There are instructions on the FIPS FIPS page, FIPS manual pages and README. One thing I will mostly talk here in the sense of performance being the speed for CPU cycles, but this slide shows you how you can reduce the footprint also of the OpenSSL library for devices with constrained memory. So if you want to obtain a build of OpenSSL that supports minimal TLS implementation with reasonable compatibility and performance, you can use these long list of no-something options, which will disable these features that is actually not really needed for general like TLS client or server, which does not need to support something else than TLS. And you can see that the libcrypto, at least in my build on x86-64, gets smaller by 33% and libSSL by 42%. The other topic that I'm covering here is optimizing EVP API usage. As I said, the following sections I will be mostly talking about optimizing for speed in CPU cycles, not for other measurable attributes such as code size. With support for providers, there is much greater flexibility and larger feature set. However, that comes at some costs. We try to maximize compatibility with old application code, and having things like default lib context and lazy initialization, which basically means that more locking is needed, and that affects multi-threaded performance. There is also this implicit algorithm fetching, which means that because fetch is not a free operation, the implicit fetching will cause the fetch operation to be repeatedly performed if you don't prefetch, and for better performance, repeated fetches should be avoided. We kept support for engines and low-level methods, which is not that bad for performance because that just raises the library footprint. It should not affect the performance directly. So let's start with some concrete code examples. Let's try to digest, for example, 64 bytes with SHA-256 repeatedly. All the numbers that I will be talking about here about the time for operation, for some operation, were measured on my AMD Ryzen-based laptop with OpenSSL-331 version. Here, I've always measured the time to execute this loop with some high number of num calls, and then divided the total execution time by num calls. I've executed the testing executable multiple times and averaged the results. So here we inside the loop, which is executed, which has like a high number of iterations. I'm allocating the EVP MD CTX. I'm calling digest in it with a EVP underscore SHA-256, which is a implicit fetch. The EVP underscore SHA-256 is a constant object that's just a placeholder containing the name of the hash function. And then in the loop, we call digest update with one message of 64 bytes and digest final to get the resulting digest. And then we free the context. Of course, this uses the implicit fetch, and I measure that this will take 0.386 microseconds per one digest operation, like per one execution of the cycle in average. So this can be improved by using explicit digest algorithm fetch. We call EVP MD fetch instead of using EVP underscore SHA-256 function. And the rest of the for loop contents is the same. After we are done with looping, we need to free the fetched MD object, EVP MD object, because that's allocated object. It's no longer constant. And for this case, I obtained 0.238 microseconds per one loop, which should be roughly equivalent to 111. There is no extra locking or anything there once you fetch the EVP MD. But we can optimize a little bit more because we don't need to allocate and free the EVP MD CTX object inside the loop. So if we put these outside of the loop, we just can reinit the object in the loop. This will take only 0.198 microseconds per one digest operation. With encryption, we can do some more. Let's try to encrypt 1 kilobyte of data with AES-256 CBC algorithm. Here we call encrypt update just once in the loop, inside the loop. You could have some applications of when you are encrypting large data that you would call encrypt update between the init and final multiple times. If it is necessary to encrypt some large data, it is always faster to call EVP encrypt update less times on larger chunks of data than more times on smaller chunks, but that's fairly obvious. So here we continue on the previous examples from the digest EVP MD. We fetch the cipher algorithm with EVP cipher fetch, allocate the EVP cipher context, and inside the loop we do EVP encrypt init x2, then encrypt update, encrypt final x. This will take 1.161 microseconds per one encryption operation of this 1024 bytes. But there is something that can be optimized. There is something where we are wasting computation time. We can reuse the preset key schedule, because when we init, we call EVP encrypt init with some key data. The key schedule needs to be created or expanded for the actual encryption, the AES algorithm, or with the AES algorithm. So we call EVP encrypt init x2 with just the fetch cipher and the key outside of the loop, but inside the loop we always just call EVP encrypt init with null cipher and null key and with a different IV. Here I expect that for every message that you encrypt, which is like usual in security protocols, you use the same key, but you use different IV. If you are communicating with some peer where you pre-establish the key. And this optimization will help because it will take just 0.938 microseconds per one loop execution, one loop iteration. Then, what about the composite algorithms such as HMAC, HKDF, and so on? These composite algorithms are composite because they use internally some other algorithm, some more primitive algorithm, such the HMAC is composed of digest operations. Yeah. So it uses internally HMAC-SHA-256. So uses internally the SHA-256 digest, which has to be fetched by the provider actually. So here we fetch the MAC algorithm, allocate the MAC CTX, and prepare the parameter with the hash algorithm name, digest name, which will be SHA-256 here. And then we, inside the loop, we initialize the context with the parameters array and update, basically compute the MAC of the buffer, which in my case, it was 200 bytes in this example, and finalize the MAC. This takes 0.741 microseconds per computation and per iteration. However, there are also some inefficiencies. because the SHA-256 digest algorithm is internally fetched in the HMAC implementation. So can we do better? Yes, we can create a template context and duplicate it. So here we again fetch the MAC, HMAC, create a template context, pre-initialize it with a key and these parameters containing the SHA-256 digest name. And inside the loop, we always first duplicate the context, which was pre-initialized with the key, and call the update on the buffer that we are computing the HMAC for, and finalize it. This takes actually 0.699 microseconds on my machine per computation of this HMAC SHA-256 of 200 bytes. There is another possible optimization where, actually, no. If the key is different, here we used always the same key, but if the key is different, we could still try to use the duplication trick, but we would not. We would just init the HMAC with null key, and then reinit it inside of the loop with the actual key. I'm not showing the code here. It's left as exercise for the readers or like watchers of this webinar. However, the context duplication overhead is larger than the internal fetch actually, so this requires 0.921 microseconds per the iteration, which is, I'm going back here, it's higher than the original. So this is actually not helpful. My next area that I wanted to cover is about optimizing usage of some Libssl APIs. In TLS client, if you always should create and preset SSL CTX with the CI store, and this is used for creating the SSL objects for connections. It's always better to use the same SSL context with multiple client connections instead of creating it repeatedly for every connection. This requires, for my measurement, it requires 995 microseconds instead of 1100 microseconds to do handshake when the client SSL context is shared. So the overhead for creating the SSL context and populating it is presetting it is like 10%, around 10%. It's a good idea to use cert directory store instead of the cert file store for CA certificates, because the file format or the format how the certificates are stored in the store doesn't require, if you use the directory store, it doesn't require to load all the certificates when the store is initialized. Because the directory store is done in a way that it contains the file name contains a hash of the certificate subject name, and that helps to load only the certificate that is needed to verify the trust or build a trust chain. I unfortunately don't have any benchmark numbers. It highly depends on how big your CA cert or trusted root store is. Of course, like if you have like only a few certs in the root store, then it won't be much different. But for if you have like hundreds of certificates there, it really makes a difference. Then I wanted to talk about SSL session reuse on the TLS client. This is a complex topic, probably for a separate webinar session on advanced Libssl API usage, but I wanted to at least shortly talk about this. SSL session caching is enabled by default on the server, but not on the client side, because, and the reason is that even if enabled on the client side, which you can do, the Libssl will not use the cached SSL session entries automatically, as only the application knows when the session can and should be reused. There is one exception when Libssl actually reuses the session, and that's when an SSL object is reused for a subsequent connection. So there is already SSL session present in the SSL object, and it will be used if accepted, if resumable and accepted by the server. You can use SSL get one session and SSL set session functions to obtain and set the SSL session objects from SSL, but preferably for getting the session objects, there is a new session callback that should be used. But as I said, this is complex topic, and yeah, basically what I wanted to say here is that, yeah, reuse sessions, but you will have to add application code for, or application session cache for reusing session on a client. If your application is server, this is done automatically by Libssl. Another thing to optimize for Libssl is it's not really about API usage, but about like usage or setting up the SSL connections, is to avoid using expensive key exchange algorithms. For that, you can or what I mean by that is that you should disable RSA and DHE key exchanges. For TLS 1.2, you will do that by SSL's CTX set cipher list call. And this cipher list string default colon -k RSA colon -k DHE will disable or remove, will use default list of ciphers, but remove RSA and DHE, plain DHE key exchange. For TLS 1.3, which is not affected by the cipher list string, we need to list the allowed groups. For example, we can use SSL set one groups list with this list of groups which don't include any DH groups, those FFDH groups. Here I have X25519 in front of P256. The reason is that there are some properties of X25519 which make it like better from a security perspective, but whether X25519 is faster than P256 depends on the platform. For example, on my laptop, one X25519 operation takes, or the key exchange takes 27.5 microseconds, where P256 takes 41.2 microseconds. But X25519 is not FIPS approved. So if your requirement is using FIPS approved algorithms, then you cannot use this. So I started already on the topic of choosing the most performant algorithms. I would say, yeah, never put performance over security. But is it really like so strong that you really never should do that? Should I always use crypto with at least 256-bit security because that's like less performant, more security? Yeah, but that would be silly. So better idea is to say stick with some minimum security level depending on your requirements. If you don't do any military or long time security things, 128-bit security should be sufficient for most use cases. And of course, use the right algorithm for the job. AES ECB mode encryption is fast, but never the right answer. Yeah, and the ECB mode cipher is basically the raw building block for the other more useful modes, and it provides a key permutation function for cipher block size data, but no, it's not usable for normal real life use cases. It would be completely unsecure to use it. And everybody knows that inventing your own cipher is nonsense because you won't do it right and it won't be safe unless you are some crypto expert. However, and even crypto expert needs peer review or multiple other crypto experts to actually verify that their idea was good. But however, the same thing applies to cryptographic protocols and formats. So you should use TLS and QUIC for data transfer, encrypted, authenticated, and so on. Or CMS if you need to send some encrypted messages, or protected messages. But even with the previous slide on mind, which algorithm should I use to symmetrically encrypt some raw data? Here I'm only testing AAD ciphers to protect both confidentiality and integrity of the data. And to measure, I use the OpenSSL speed -EVP command. The OpenSSL speed command will show you multiple different speeds based on how big blocks of data are encrypted with a single encryption operation. Here I'm showing only the data for 16 kilobyte blocks. And interestingly, you can see that for me, the AS128 OCB is the fastest one with 9,000 megabytes per second encrypted. And the slowest one is CCM, Chacha, or GCM is the second, and Chacha the third. However, the results might be very different on different CPU architectures, and even different CPUs on the same base architecture. For example, CPUs without AES-NI, the Chacha 20 poly 1305 algorithm will be the fastest one by a large margin. And also more secure because without AES-NI, there might be side channels and so on. You can use OpenSSL speed to measure not only speed of ciphers, but also digest, signatures, key exchanges, and so on. So which algorithm to choose for certificates? We can use OpenSSL speed again to measure RSA versus ECDSA and EDDSA. You can see here that ECDSA with the NIST P256 curve is actually the fastest for signature operations, and by fairly big margin. The EDDSA is the second one, possibly because it's not so highly, the implementation in OpenSSL is probably not so highly optimized. I think it could be optimized a little bit more. For verifications, we can see that RSA is actually fastest, although RSA 2048 does not have security strength of 128 bits as these ECDSA with NIST P256 and EDDSA with ED 25519. For that, you will need RSA 3072, which is even slower, but still the verification speed is quite good. So which algorithm should you choose for certificates? For maximum speed on the server side, we want to use ECDSA with NIST P256 parameters. That's from those measurement, it's obvious. In theory, the RSA keys, even with 3K size, to achieve the 128-bit security level would be better for CA certificates for roots or intermediates, as the speed of verification is better for RSA. However, this does not account for larger data transfer size for the intermediate CA cert chain, which can probably, depending on how fast the data transfer is, it can change the numbers of real-world connection speed. EDDSA and also the speed of the verification is important for the client side only. EDDSA has some better security properties than ECDSA, and as I said, could be probably optimized further, but currently it is slower than ECDSA. So for maximum compatibility, we can have both ECDSA and RSA certificate on the server. So how do we set the server up in the way to prefer the ECDSA certificate if the client supports it? For TLS 1.2, we need to order ECDSA ciphers before the RSA ciphers. To do that, we actually have to explicitly list the ciphers that we want, the groups of ciphers. So the A ECDSA and A RSA in this cipher list string, they are explicitly stating ECDSA ciphers first, RSA ciphers second. And we remove all these because if you do the string, if you do the cipher list this way, this will add all the various key exchanges, and I've said before that we should probably drop RSA key exchange and DHE key exchange. So we use -K RSA, -K DHE, and enull, that's null encryption. It actually would not be used really, but just for correctness or to ensure that it really wouldn't be used, we use -enull aria Camellia, we don't need these ciphers because they are not really used. For the TLS 1.3 side, we need to set SIGALCs. Here we use the SSL CTX advanced SIGALCs list function and the SIGALCs string. I've took it from Fedora crypto policies. They are in the form of public key algorithm and digest separated by plus or in the TLS 1.3 style named signature scheme. And the last thing that you need to do to really prefer the ECDSA over RSA is to set the server cipher preference, SSL CTX set options, SSL op cipher server preference, which affects both ciphers and SIGALCs to prefer the what we set on the server side and not what the client sends to us. And this is the last topic here. For further reading, I recommend especially the API reference manual pages, the command line applications reference. Look at the webinars if you didn't see them, the previous ones. And yeah, there is also interesting to read, or if you want to know something more about block cipher modes, to read the wiki page, Wikipedia wiki page.
So as a reminder, this webinar is being recorded and will be made available on our YouTube channel shortly after the presentation. If you have any questions or comments, please feel free to email us at feedback, that's feedback@openssl.org. If you'd like to receive a copy of the slide deck, you can also email us and we'll be happy to send that over to you. It will also be sent out in the follow-up email that everyone will receive after this webinar. Also, in the follow-up email, you will all be receiving a feedback form. We'd love to hear back from you and hear, what you thought of this webinar and any ideas you have for future webinars and all that sort of stuff. So it'd be great if you could fill that out. Thank you, Tomas, for a fantastic presentation, and thank you everyone for attending. I hope you all have a fantastic rest of your day.
Thanks everyone for joining this webinar and listening.